This lesson looks at horizontal projectiles. So if we launch something, through the air, how does it fly? So a projectile is a fancy name for an object that's in free fall. Typically, it's in free fall near the surface of the earth. And it's typically moving in two directions, horizontally and vertically. But an object just moving vertically in free fall is still a projectile. It's just a boring projectile. Projectile problems are just 2D kinematics problems. So exactly like we saw in the last lesson, start by determining a start and end point. Break your vectors into components. Solve the relevant kinematics equations. And combine back if necessary. One thing that's super important to realize is that delta t is the same for both directions, horizontally and vertically, right? This is why we pick a start and end point, because between the start and the end, the same amount of time has to pass, because the start and end are those fixed points in time. Easiest way to see this is just by starting to look at examples here. But before we get to that, one thing to mention is for horizontal projectiles, the initial velocity in the y direction, so v subscript y 0, so the initial velocity in the y direction is always 0 meters per second. This is only for horizontal, because if we launch something horizontally, it's not moving up or down to start. Okay, let's look at an example. Sorry, I don't know why that problem-solving method got stuck in there. A projectile is launched horizontally off the top of a cliff with a speed of 10 meters per second and strikes its target 3 seconds later. How tall is the cliff, and how far away is the target from the base of the cliff? So we sketch this out. We don't know how tall the cliff is. We don't know how far the target is. Which I'll just draw a box here. We do know that the projectile is launched with an initial x velocity of 10 meters per second. And we know it has an initial y velocity of 0 meters per second. Because all the velocity is horizontal, that means it's all in the x direction. There's none in the y direction. We know that a equals g equals 9.8 meters per second squared. And I'm actually going to call this positive because I'm going to do something a little interesting here and call down positive and up negative. And that'll just mean that I can deal with all positive numbers. I don't have to worry about negatives. We also know that delta t is equal to 3 seconds. So we've got everything in components already. I've got my displacement in y's and x's. I've got my velocities in the x direction and the y direction. I've got my acceleration in the y direction. There's no acceleration in the x direction because it's in free fall. Nothing's pushing or pulling it. It's just traveling along. So let's start looking at it. Well, if I want to find an x displacement, and I know that the acceleration is 0 and I know the initial velocity, I'm going to use this equation right here. But we know that this term will all be 0 because the acceleration is 0. So delta x just equals the vx naught times delta t, which will be 10 meters per second times 3 seconds, which means that delta x is equal to 30 meters. Nice and easy. The delta y is going to be a little trickier, but not too bad. It's got a v naught y delta t plus 1/2 g delta t squared. This term is 0, so delta y is equal to 1/2 times 9.8 meters per second squared times 3 seconds squared. So that's going to give me roughly 10 times 9, which is 90. So delta y is approximately 45 meters. Notice that the second squared will cancel with the second squared, and I'll be left with just meters. And the delta y is a positive number. And how did the ball move? It went down, which in this case is positive, so the signs match. And that's all we have to do for this problem. Okay, and for the second example, imagine you're on top of a 15-meter tall building. If you want to hit a target on the ground 30 meters away with a horizontal projectile, how quickly must you launch it? So we've got a building. We know in this case, this time we know delta x equals 30 meters. We know that delta y equals 15 meters. I'm again going to use down as positive and up as negative because in this case we're only moving down, so it makes sense to call down positive. And we launch this with some initial unknown velocity in the x direction. But because we're launching it horizontally, we know the y initial velocity is 0 meters per second. We know the acceleration in the x direction is 0 meters per second squared. And we know that the acceleration in the y direction is equal to g is equal to 9.8 meters per second squared. And we don't know the delta t, it wasn't given. Well, let's just start by let's start by looking at how could we find the initial velocity. Well, I know that the initial velocity times the time plus 1/2 ax delta t squared, which this whole thing equals 0. So in other words, the initial velocity in the x direction should be the change in x divided by the change in t. Which is great, except we don't know delta t. But if you remember back to earlier, I said delta t is the same in both directions, between the start of the ball at the top and the end of it hitting the target. So let's look at our y direction. Delta y is v y naught delta t plus 1/2 g delta t squared. This term is 0. So we have delta y times 2 divided by g is equal to delta t squared, or in other words, delta t is the square root of 2 delta y over g. And that can be plugged in here so that we get Vx naught is equal to delta x over the square root of 2 delta y over g. And at that point, you can just plug things in and find out, what it is. But let's check our units real quick first. 2 delta y over g. Delta y is going to be meters. G is going to be meters per second squared. If you flip that over, you end up canceling your meters and getting seconds squared. In this square rooting it gives us just seconds. We have meters on the top, seconds on the bottom. Units check out. This bottom will have to be positive. Delta x is positive. That means we have a positive velocity. That checks out. If we had a number, we could see if that seems reasonable. Eyeballing it though, delta y will be 15 over g is about 10, so 30 over 10 is about square root 3. So Vx naught should be approximately 30 over square root 3 meters per second, which is bigger than 2, probably close to 3. When you actually calculate it, 2.6 something, I don't know. I'm throwing that number out there, but you can check that yourself.